Dear student, welcome to this session. In this session, we are going to see some problems based on the EMF equation what we derived in the last session. Before we start with the problems, just we'll go through the summary of what we have done so far. Three-phase synchronous generator or alternator or AC generator is a electrical machine which converts mechanical energy into three-phase AC electrical energy. So it will convert a mechanical energy into three-phase AC electrical energy. So that is called as a synchronous generator or alternator or AC generator. And what is the principle of operation? It works on the principle of electromagnetic induction. That is, whenever a flux linked with a coil or conductor changes, an EMF is induced. That is the principle of operation on which this particular alternator works. And also we saw the construction. The main parts of the alternator are stator and rotor. The stator is the stationary part or the static part of the machine, and rotor is the rotating part of the machine. And there are two types of rotors we saw. One is called as a salient or projecting pole type, and another one is a non-salient or a cylindrical pole type. So this is the construction we saw. This is the stator, which is the outer part, and inside we have the rotating part, that is called as a rotor. And on the stator we have the armature winding, and it is a three-phase star connected winding. So these are the three phases R, Y, B. And inside we have a rotor which is mounted on a shaft. It rotates on the shaft. And on rotor, again there are two types, salient and non-salient. On salient or non-salient, we have a winding that is called as a field winding, and that field winding is given with a DC supply. That is the supply we give to the field winding, and that field winding is connected to this DC supply through the slip rings and the brush arrangements. And how does it work? Whenever we give the DC supply, electrical current will flow through the field winding through the brush and the slip rings. When electrical current flows through all this field winding, it will create a magnetic field. So each pole will act as a north and south, so they will be alternating. So we will be having north south poles alternating, and the pole will be always in a pair. So number of poles is always in pairs, north and south. When this particular rotor is rotated with the external mechanical energy, all the armature winding conductors are static. They will start cutting the magnetic flux. And we know that whenever the flux linked with a coil or conductor changes, an EMF is induced in all those conductors, and we have three phases of the winding. The conductors are connected in three phases, so it will generate an output of three phase. That is how we get the three phase output. So construction, again we have a salient pole type. So this is the salient pole type, where we have the projected poles, and it will be alternating, north south will be alternating. We looked into the advantages and disadvantages of this particular type of a pole, and also we saw the non-salient pole. In case of a non-salient pole, we do not have any protruding poles. The poles, this structure is a cylindrical, and we looked into what are the advantages and disadvantages of this particular type of a rotor. Then we looked into equation of frequency. Okay, so what is the this derivation, very small derivation, which is important. So the frequency of the induced EMF will depend on the rotor speed, how the rotor is rotated, with what speed it is rotated, and how many poles will be there on the rotor. So it will depend on that, and we did the derivation. This is a important equation. We get it, F is equal to N into P divided by 120, represented in cycles per second or hertz. So frequency of the induced EMF or the generated EMF is given by F is equal to N into P divided by 120. N is the rotor speed, and P is the number of poles. Then we looked into the EMF equation derivation. So EMF equation derivation, we get it as it is represented per phase. You have to remember ERMS per phase. So ERMS per phase is given as 2.22 kp kd f phi z. And what is kp and kd? Those are the winding factors. Kp is the pitch factor and kd is the distribution factor. F is the frequency, phi is the flux per pole, and Z is the total number of conductors per phase. ERMS per phase is represented by this equation. So in today's problem, we are going to solve the problems. We will be using this equation, and if instead of number of conductors, if number of turns are represented, each turn will have 2 conductors. That time the equation will become ERMS per phase is equal to 4.44 kp kd f phi into T, where T is the number of turns. Winding factor, what is a winding factor? We have distribution factor and the pitch factor. Kd is the distribution factor. It is the ratio of EMF with the distributed winding to the EMF with the concentrated winding, and this is the formula that we should remember. Then pitch factor Kp, Kp is equal to a ratio, Kp is the ratio of EMF induced in short pitch coil to EMF induced in the full pitch coil, and this is the equation. Now we will see some problems. Now we can see this problem. A 3-phase 50 Hz star connected alternator has 180 conductors per phase. So what is this? Z is equal to 180 conductors per phase, and flux per pole is 0.0543 Weber. The flux per pole phi is given as 0.0543 Weber. What we have to find? We have to find EMF generated per phase. Second one is EMF between the line terminals. So you have to remember it is a star connected. So EMF between the line terminals. Assume the winding to be full pitched and distribution factor to be 0.96. What is winding to be full pitched? So we know the pitch factor, that is a Kp. Whenever the winding is full pitched, Kp is equal to 1, and the distribution factor Kd is equal to 0.96, and we know the equation of the EMF per phase. So RMS value of the EMF generated per phase, E phase is equal to 2.22 Kp Kd Z F into phi. Kp, they did not give the Kp directly. What they have said, assume the winding to be full pitched. Whenever you see the full pitch as the word, if the coil is full pitched, then Kp becomes 1. Kp is equal to 1, and distribution factor Kd is given as 0.96. Z, what is the Z? Number of conductors per phase. That is also given, 180 conductors per phase. And F, frequency, is given as 50 Hz. And phi, what is phi? It is a flux per pole. Flux per pole is given as 0.0543 Weber. If you substitute all those values and if you calculate, we get the E phase, that is the EMF generated per phase, will be calculated as 1041.5 volts. And now what we have to find? EMF between line terminals. What is this? They are asking the line voltage. What would be the line voltage in case of a star connected system? We already did that derivation. The line voltage would be √3 times the phase voltage. Therefore, line voltage EL is equal to √3 times E phase, and that is equal to √3 into E phase. We already calculated as 1041.5 volts. So we will get it as 1803.93 volts. That is the line voltage. That is how we solve this particular problem. We will see the next one. Next one, find the number of armature conductors in series per phase. So you should be able to identify what they are asking. So find number of armature conductors. So armature conductor is nothing but the Z, number of conductors per phase, series per phase. So they have elaborated that particular Z description. So this particular description, armature conductors in series per phase, is nothing but Z, that is number of conductors per phase. So Z we have to calculate, required for the armature of 3 phase, frequency is 50 Hertz, number of poles they have given, P is equal to 10, alternator. So that is the alternator. This is the description of the alternator. The winding is star connected to give line voltage of 11,000 volt. So they have given the line voltage. You have to remember, they have given line voltage, what we get as a output of the alternator. The flux per pole is 0.16 Weber. Assume Kp is equal to 1 and Kd is equal to 0.96. All these things are given. Now what we have to find? Z. Only one equation we have is this: E phase is equal to 2.22 Kp, Kd, Z, F and phi. If you see, we have to calculate this Z value. First thing is, they have given the line voltage, not the phase voltage. This equation is phase voltage. So this is the voltage per phase, RMS value of the voltage per phase is given. Since it is a star connected, we know the relation between the phase and the line. What is the relation? E phase is equal to EL divided by root 3. So the phase voltage is equal to line voltage divided by root 3, that is 11,000 divided by root 3, we get it as 6,352 volt, that is the E phase. And rest of the things are, everything is given in this equation. E phase we found it as 6,352, Kp is given as 1, Kd is given as 0.96, Z is the unknown, F is given as 50 Hertz, and phi. What is the phi? Phi is the flux per pole. So the flux per pole is 0.16. That is also given. If you see, 10 pole is the additional information. If there is additional information, no problem. Z is equal to E phase divided by 2.22 Kp, Kd, F into phi. We substitute all these values and we get the number of conductors as 372.5. So we cannot have the number of conductors as a fractional number, so we can round it. So you can take it as a round number as a 372 conductors as a number of conductors that would be required on the armature. We'll see the next problem. In the next problem, the armature of an 8-pole 3-phase 50 Hertz alternator has 18 slots and 10 conductors per slot. So here what? The armature of 8-pole, number of poles P is equal to 8 and it is 3-phase. F 50 Hertz, frequency is F is equal to 50 Hertz. Alternator has 18 slots. So I told you, the on the inner periphery of the stator we will be having the slots. How many slots are there on the inner periphery of the stator? 18 slots are there and 10 conductors per slot. In each slot, how many conductors are there? In each slot there are 10 conductors. So 10 conductors per slot. So 18 slots, and in one slot there is 10 conductors. How many conductors we have in total? 18 into 10. So we have total of 180 conductors. Okay, you have to remember that. Then a flux of 0.04 Weber is entering the armature from one pole. So what they have given, 0.04 Weber of flux is entering the armature from one pole, means this is nothing but 0.04 is the flux per pole. This is 0.04 is the phi. And what is the phi? Phi is the flux per pole. Calculate the induced EMF. Calculate the induced EMF per phase. So we have to calculate the E phase, that is the induced EMF per phase. And what is the equation? 2.22 kp kd f into phi. And if you see here, kp and kd is not given. The first thing we are going to do is, since those values are not given, we will assume them to be 1. So kp is equal to 1 and kd is equal to 1. If you check, they have not given the Z. What is Z? Z is the total number of conductors per phase. But what they have given? They have given total conductors. So how many slots are there? 18 slots are there, and in each slot there are 10 conductors. So total how many conductors we have? Total number of conductors is 180. Is it Z? No, it is not the Z, because Z is number of conductors per phase. And what is 180? This is total conductors. It includes all the 3 phases, but we want it only for one phase. Therefore Z, that is number of conductors per phase, is equal to 180 divided by 3, that we get it as 60. So you have to make sure that you are calculating the right values, even though the information is given in indirect terms. So they don't give the directly the Z. What is Z? Number of conductors per phase. But they have given you the total conductors, and you know how many phases are there? 3 phases are there. So total conductors divided by 3 will give you the number of conductors per phase, that is Z. We get it as 60. Now what is the equation? E phase is equal to 2.22 kp kd f into phi into Z. Z is missing, so we have to put that. Now we will put 2.22. 1 is the kp, kd is 1, and Z. Okay, Z is 60 and frequency is 50 Hertz. Phi is given as 0.04 Weber. So we get the E phase as 266.4 volts. In the next problem, a 3-phase star connected alternator on open circuit is required to generate a line voltage of 3600 volt. So a 3-phase star connected alternator, don't worry about this open circuit, it is required to generate a voltage. Line voltage is EL is 3600, frequency is 50 Hertz. When driven at, what is the speed? The rotor is being driven at a speed of 500 rpm. The stator has 3 slots per pole per phase. So how many slots are there? There are 3 slots per pole. Under every one pole there are 3 slots per pole per phase, and 10 conductors per slot, and in each slot there are 10 conductors. This information is required to calculate the number of conductors per phase. Calculate the number of poles and useful flux per pole. Okay, assume all the conductors per phase to be connected in series and coils to be full pitch. When they say coils to be full pitch, that means Kp is equal to 1. Now the equation what we have is, the first thing what we have to calculate, we have to calculate number of poles. Okay, number of poles we have to find. How we calculate that is, we know the equation of the frequency. Equation of the frequency is F is equal to Np divided by 120, and what is N? It is the rotor speed 500, and P is the one which is the unknown, and F they have given us as 50 Hertz. So in this equation, except P, all the values are given. So if you substitute all the values and calculate P, you get the P as 12 poles. So how many poles are there? 12 poles are there. what is the next item you have to calculate? Useful flux per pole. Phi we have to find. So which equation you are going to use? You are going to use E phase is equal to 2.22 kp kd z f phi, and you are going to calculate the phi. And for calculating phi, we should know all other parameters, isn't it? So we will go one by one. What are the first is we have to how much is the line voltage? 3600. The EMF per phase is we know the in case of a star connection, E phase is equal to EL divided by root 3. 3600 divided by root 3, we get it as E phase is equal to 2080. Next thing is what? We have to find the number of conductors. So we know how many slots are there per phase. See, you can see 3 slots per pole per phase. So what we want? Number of slots per pole, okay, is given. So we don't want per pole per phase, we want number of slots per phase only. If you multiply this 3 with the number of poles, that is 3 into 12, number of poles, what we get? Number of slots per phase. What they have given? Number of slots per pole per phase. So we don't want per pole per phase, we just want per phase. So if you multiply that with 12, 3 with 12, we get number of slots per phase as 36. And how many conductors are there per slot? 10 conductors are there. So number of conductors per phase, Z is equal to number of slots into number of conductors per slot. Number of conductors per slot 10. 36 into 10, 360. We calculated the Z value. Now for your syllabus, if you can remember this formula, you can calculate these are the different values given. You can calculate KD. So what is the equation of the KD? Kp is already 1. We know it is full pitch. Kp is 1. How to calculate KD? KD formula we have noted down. KD is equal to sine of n alpha by 2 divided by n into sine of alpha by 2. And what is alpha? Alpha is called as a slot angle. How to calculate that? 180 divided by number of slots per pole. That is 180. How many? What is the number of slots per pole? Number of slots per pole is 3 into 3, right? You can see here, where is the, see, this is number of slots per pole per phase, okay? We want to calculate number of slots per pole only. So if you multiply this with 3, we get, that is 3 into 3, we will get number of slots per pole. So number of slots per pole is 3 into 3, we get it as 20 degree. Alpha is 20 degree. And what is n? N is number of slots per pole per phase. That is the n value. N is 3. N is given as 3. Number of slots per pole per phase is 3. So 3 into 20 degree divided by 2 divided by 3 into sine of 20 degree divided by 2. If we calculate this, we get the value as KD is equal to 0.96. Now you can substitute all those values in this equation. E phase is equal to 2.22 kp kd z f phi. So all the values are available except the unknown phi. If you calculate, if you substitute all the values and calculate for the unknown phi, you get the flux per pole as 0.0543 Weber.